So guys, we'll be waiting for some time if somebody else joins. Okay, so let's start. So good evening. I hope all of you must be knowing what are these sessions like, kind of like why are these conducted. I think you must be knowing, right? Can you guys hear me? Hello. Are you guys able to hear me?
Yes, sir.
Great. So these are actually some problem solving sessions. So I'll be taking you through some of the topics like, so now is the introductory part going on still. How many weeks of lectures have been uploaded?
3.
Okay. So you have gone through all the lectures of 3 weeks.
The third week it is just recently uploaded today. The 2 weeks completed.
Okay, great. So have you completed the assignments for the 2 weeks?
Yes, sir.
Okay. Did you face any problem?
No,
Cool. So all of you are undergraduates or some of you are PGs also?
the BTech.
Okay. Okay, so let's go through some concepts and through questions actually. We'll be solving some questions which may clear some of your doubts or give you some additional concepts in an advanced manner out of what have already been taught to you. So in the meantime, if any one of you find any doubt or want to ask any question, you can do so. Okay. So let me share my screen. Can you guys see my screen?
Yes, sir.
Great. So, did you find any question of this sort regarding to wear mechanism? Hello.
It was covered, I think, in the assignment 1. Yeah.
Okay. So you there are many types of wears happening during machining or even during additive manufacturing processes. So these adhesive, abrasive, and diffusion wears are common ones, but there are some others like fatigue wears and corrosive wears. So fatigue wears are something like uh, happens when a particular product is subjected to some cyclic loading kind of thing. Like you can see that in rolling process, or you can see that in rotating parts in engines, motors. Okay, so when or you can even see that in case of belt and pulley mechanisms, when two parts are continuously in touch to each other and one is rotating and completing hundreds and thousands of cycles, then at some point of time, these parts come close, deform, undergo plastic deformation, their shapes changes, and they come in connect to each other, and this type of wear happens. Initially, there is a clearance gap, but with time, with increasing number of cycles, such kind of deformations happen in the products, and then they come in touch to each other, and this type of fatigue wear happens. Another is corrosive wear, which happens like when a surface is subjected to maybe open atmosphere, maybe there can be oxidations and all. The surface, the top surface can get activated, and when the other part comes in contact, that the strength and brittleness of that surface reduces due to oxidation, and this type of phenomena called corrosive wear takes place. So the question says, which of the following phenomena is not correct with respect to wear mechanism? Can anyone of you tell me? So this is an interactive session, okay? You have to answer with me. You have to try to answer. I will take you through after that. All the questions will be solved here only. But you have to interact, okay? Can somebody of you answer this question? Okay, so in chat, Bipin says C. That's correct. Cool. So this question says, in the equilibrium phase diagram, can you identify solidus, liquidus, and solvus lines? Phase diagram has been taught to you, na?
Yes, sir.
Can you identify these lines? Do you know what solidus, liquidus, and solvus lines means?
So no picture is visible, only the text can be seen.
No, I am asking you if you know solidus, liquidus, and solvus lines. Do you know? Can you define them? After that, I will show you the diagram.
So the solidus line separates, like, is a boundary between the liquid plus solid phase and the solid phase. And similarly, liquidus line is the boundary between the liquid and solid and the liquid phase.
And what is solvus line? Anybody? Okay, so see. So what Sahil told was kind of correct, but in simple words, in simple language, you should know that a solidus is defined by the line which is drawn at the temperature at which melting begins. The first liquid droplet is formed. That is called a solidus line. And similarly, in case of liquidus, it is a line in which like that separates the liquid phase from a solid and liquid. Like there should be a exact difference at the boundary. There should be some small crystals forming above or below the boundary. Such a line is called a solidus line, sorry, liquidus line. And then comes a solvus line. That is an interesting thing. Like that happens in case of, like, you see this diagram. So this line is called as a solvus line. Sorry. So this line is called as a solvus line. Why? Because like here, what happens is the concentration of carbon is increasing. And at a particular point, it again starts reducing. Okay. So this alpha phase of iron, which is having the maximum percentage of carbon at this particular point, this is probably 0.83% of carbon. So this particular point is up to this particular point, this line differentiates between same phase but two kind of microstructures. Like here, the ferritic iron has one microstructure, and on the right hand side, it is having a different microstructure, but both are in solid phases. So such a line is called solvus line. Okay. So such kind of questions, see what has been taught to you or will be taught to you directly, from those topics you may not directly find questions in the exam. So these small topics related to what has been taught, you must know. Yeah, this PPT will be shared. So this is the common iron carbon phase diagram. Here you can see, I have already shown you this particular solvus lines, then this solidus lines, liquidus lines. So from these lines, actually, you can understand like where is the phase transformation happening, where the phase is same, but microstructure variation is coming, like those kind of things. So this is for your reference. We'll come to it back if it is required afterwards. Okay, so this is a question. It is saying like which of the following is not true for eutectic point in the equilibrium phase diagram? And somebody of you answer. Do you know which one is the eutectic point?
Liquid gives two solid phases.
Yeah,
The deep option D.
true, correct. So, Sriram, your thing is not right. It's being said which one is not correct. And can you, Sriram, please speak over uh, other than writing chats? So, how much iron is there in the cementite? Uh, can you please tell me?
Around 6.7%.
Okay, but why is it so? Like, why is the phase diagram limited to that particular percentage of carbon?
Sir, if the alloy exceeds that amount of carbon, then the material cannot be used for any engineering application.
Why so?
So it becomes very brittle. With the increase in carbon content, material becomes brittle.
Okay, but brittle materials are still used, na? So, have you heard about graphite? What the pencils through which we write, that's made of graphite actually. So after 6.67% carbon, what happens is graphite starts to form. So graphite has a unique structure like that. You can see in the screen. What happens is there are strong bonds in a particular layer. So graphite is a layer-wise structure. Graphite has a layer-by-layer structure, but in every layer they have strong bonds, covalent bonds. But the bond between two particular layers is really weak. So what happens is when you give a shear force, you guys understand shear force. So you all are in which year now of undergraduate?
Second, fourth sem.
Okay, so you have covered some
Yes,
strength
sir.
of materials. Okay, so when you give a shear force, what happens is it's like there is very little resistance between the two layers of atoms, and one layer starts sliding over the other. So as a result, a slippery kind of contact happens in between two, and there is very low resistance. So what happens is you just cannot use it for any structural applications. You can still dope it with some other alloys or some other dopants and increase the resistance capacity of the graphite, and then you can use it for some structural applications too. These days these are being applied in automotive and aerospace industries by using dopants, but directly you can't use graphite. So what happens is after 6.67% carbon, this graphite structure starts to form, and these materials become really unusable for structural applications. So that's the thing. So this is a question. It doesn't require any concept. You have to remember this kind of tables where uh, you know, like there are heat treatments and alloying treatments on metals to make them usable for specific or like a particular specific usage. When, like for example, when you need to use steel in an aircraft or jet engine, what you require is it should have high resistance in high temperatures. Like in jet engines, a very high temperature is reached. Okay, sometimes around 700, 800,000 degrees also. So at a such high temperatures, as well as in cryogenic temperatures, like much below the solidification temperature, freezing temperature, sub-zero temperatures, there the material should hold good strength. Okay, for that, which material you should dope? Okay, or if you need to rather increase the ductility or toughness of the material, then which should you dope? You should know. So can you guys relate this table and answer like which option here is incorrect? Anybody other than Sahil? Yeah, correct. So manganese, what does it increases strength of steel. So that directly means that it is going to reduce the ductility. So in this question, it says which one is the hardest form of iron carbon alloy here? Do you know about these forms from the phase diagram?
Austenite is gamma ion.
Yeah, I'm asking which one is the hardest here. So Serum has written in the chat. Sriram, do you have any problem with the mic? You guys please speak up. That will be better now. Because looking up at the chat again and again and answering, it's difficult. Yeah, so martensite happens to be the hardest. But do you know how martensite is formed, or how perlite or danite is formed? And what does this diagram represent? Has this diagram shown to you? Has this diagram illustrated to you?
Yes, sir.
Okay, so you must be knowing how martensite is formed. No? This is an austenitic structure, austenite form of iron or gamma iron, which is there. Now, what you want to do is, uh, like for reaching austenite, you have to go beyond 747 degree, right? So you can know that from the phase diagram. You need 747 degree for the first austenitic crystal to form. So now what happens is you need to cool it down back to form a usable alloy structure. Na? Now, so this diagram, how this diagram has been formed is like at every particular point on the left side of the S curve, what happens is this is the point where the particular deformation begins. Okay, and on the right side is where the deformation ends. So sorry, I mean transformation. Transformation begins and transformation ends from a particular form to another form. Now, taking up such points continuously at different temperatures, we finally get this type of curve called S curve. Okay, now suppose austenite is being like we have heated iron to austenitic form and then we cool it down. Now, depending upon the cooling rate, the different types of structures like perlite, benite, martensite, whatever is formed. Now, if the cooling rate is high, like you know what is the process where a high cooling rate is obtained is called? Anybody? So that is called quenching. Like if we quench austenite directly at a high cooling rate, so that happens is the grain structures doesn't get enough time to recrystallize. Like recrystallization, do you know, Mr. Rajesh? Okay, so what happens is like there are new crystals being formed. So there is a nucleation at a particular point, a particular nuclei of a crystal is formed, and from that it keeps on spreading, and there is a recrystallization process, and new crystals of a particular other form starts forming, other phase. So here what happens is when a high cooling rate is used, we directly get into martensite. So because the grains doesn't get time to recrystallize, so these are very small. In other words, small grains means high hardness. We'll come to why this happens later on. But for now, you know, small grains means high hardness. So here, martensite has the smallest grains of all because the cooling rate is very high and grain size is directly associated to the rate of cooling. So that's why you get martensite. Now, if we slow down the cooling process or we do step cooling, like we bring down austenite to somewhere around 600 degree and then hold it at that temperature, then we move to the right hand side of the cooling curve and we get benite. Similarly, if we hold up to 900, if we bring down to 900 and hold and to air cooling, then we get into perlite. So like this happens. Okay. A martensite is a very hard structure and it cannot be again used for some structural application. So we need to use some heat treatments or alloy treatments from martensite. So heat treatments, have you been taught? Heat treatment processes like annealing, normalizing, those kind of things.
In brief.
Sorry?
In brief, like not much in detail.
Okay. So martensite, when we obtain, we cannot use it further. So we need to temper it. There is a process called tempering, in which we again expose martensite to heat a little higher temperature than the martensitic structure, where we can get benite or perlite as per the application requirement we get. Okay. So this is a question like, so shrinkage allowance, you know, right?
Yes, sir.
So do you know which type of shrinkage requires the most attention? Like which type of shrinkage happens to be the highest shrinkage happening during casting process?
From the freezing temperature to the room temperature.
Yeah, so solidification shrinkage. So this is a question where shrinkage allowance is given. A very simple question it is. Can you find the ratio? Tell me of the particular pattern volume and the casting volume. Can you directly see it and answer without using pen and paper? No? So to look at the solution, so it's very simple. You like what I will suggest that you don't solve it by hand. Okay, you just look at the question and try to solve it directly. So this would help somebody of you, someone of you. Actually, all of you must be appearing for GATE after graduation. So there, this type of question comes. Actually, this particular question is a GATE question only. You have to just look at it and tick. You need not do it. Yeah, so what is shrinkage? Shrinkage means the material just what happens is contracts after the at the solidification range. So you have to have the pattern to volume ratio less than 1, right? So then only after shrinkage, I mean the casting volume should be more than the pattern, right? So when there is 1% shrinkage, there should be, because this is a volumetric term, it is a dimension comes in cube. There is a cube. So whatever the shrinkage allowance is given, you should get to its cube. So 1% means 1 minus 0.01 is 0.99. So you can directly look at the percentage and tick. Don't do such type of questions by hand. So now comes this question. Can you guys tell me what type of gating would be the most preferable if you are given a choice? Admin, Mr. Admin, are you there? See, this session is for you. Please interact. Otherwise, it's a bit dull session, no? Mr. Rajesh, nobody?
So horizontal grating,
There is nothing called horizontal gating actually.
actually I'd seen it in a book. So
No, this is not that. This is called as bottom gating. Gating, how can horizontal gating happen? Can you make a particular liquid flow just at level surface? You can't, right? So this is called top gating, where you put the material from the top. Bottom gating means it comes out from the top, attains it, then goes from the bottom and goes bottom up towards the top of the casting. Now the issue is there is some problems related to bottom gating also. So for that we cannot directly use bottom gating always. Like in case of top gating, we have a high erosion percentage there because the kinetic energy of the metal is very high. However, in case of large castings or castings which have very long height, such type of gatings are like unavoidable. You can't use that type of gating because the time would be much higher in those cases, and those won't be economic. Now, top gating offers something called favorable thermal gradient. Do you know what favorable thermal gradient means?
No, sir.
Okay, so what happens is in case of top gating, the material is being poured from the top. Now, what happens is the hottest material, like the metal having the highest temperature, is always on the top surface, right? Solidification begins from below, you are pouring, and the molten metal is reaching the bottom surface of the particular casting volume. There it is coming in contact to ambient temperature and it is getting solidified. Its temperature is getting reduced. Now progressively from bottom to up, the temperature is getting higher and higher and higher. The material is always being poured above the material layer with a lower temperature, right? Do you get what I'm saying?
Yes, sir.
So what happens in case of bottom gating? Tell me. In terms of this thermal gradient, what type of thermal gradient is there in case of bottom gating? So the opposite happens. Here the top layer is having the higher temperature, and here you will have the bottom layer having the higher temperature, isn't it? So what happens is there are some defects arising out of that unfavorable thermal gradient. These defects arise due to things like uh, before the inside part is solidified, the circumference gets solidified because we are pouring from the bottom, and the bottom is always in touch with the ambient. Okay, so the top remains hot and the bottom gets solidified. So in the inside, there is a lack of feeding of molten metal. So this bottom gate system produces some defects out of that. These are called as misrun or cold shut in case of casting, which we will be reading, which will be taught later on. So that's the major problem with bottom gating system. So there is a trade-off between top and bottom. However, in bottom gating, there are always least erosion, almost negligible erosion thing. So for that, what we go is parting gating system. It's called as parting line gating system, in which you take a trade-off and make the gate somewhere in between at the midway between the casting. So what happens is the top acts like a bottom gate, the below bottom acts like a top gate. So as a result, we get somewhat trade-off between the erosion thing and also this temperature gradient thing. So overall, this parting line is the best preferred gating system used in casting. So if such a question comes in future or anywhere, you remember that parting line is the most preferred gating system. So this is a question from phase diagram. You have to find out the solid composition and the liquid composition out of it. So the question says it is a binary alloy made up of copper and silver. Okay, so it is having 28% copper and the remaining 32%, 72% what is called silver at a temperature of 779 degrees centigrade. Now you have to find out what will be the two phases. The particular alloy has two phases, A and B, both of which are made up of copper and silver at a particular composition of each. You have to find out what will be the amount of A and B 779 degree temperature. So this is one of the most important questions from material science perspective. Of course, this comes in casting, but in case of material science perspective, we'll obviously find such questions. And this is This is a question which solves like if you can solve this, you can solve 90% of questions related to phase diagram uh, problems. So I will show you the diagram of this particular question. Can you please try to solve it? So Sahil, you are from which college?
Sir, I'm from NIT Goa.
Okay, great. And the others don't seem like to talk anything, right? So I haven't introduced myself, I think. So I am Ranmay from IIT Kanpur. I'm a PMRF scholar at IIT Kanpur. Uh, so this is a part of my TA duty for the PMRF fellowship. And this has been introduced by the NPTEL Council in collaboration with PMRF. Like you guys don't get exposure to live teaching in NPTEL platform. So many of your doubts get unsolved or unanswered, maybe. So this was a thing sort of decided collaboratively by the PMRF Council, PMRF and that NPTEL Council. That why don't we start such live sessions, problem solving sessions, which can help the students. And we got a good response last year. So this year also it has been continued. So are you trying to solve this problem or not? Anybody? Sriram, are you trying to solve? Okay, not in the mood to talk. No problem. Okay, so this is the phase diagram that comes out of this information. We have an alpha phase, we have a beta phase. Can you guys see my cursor? Sahil,
Yes,
can you see
sir.
my cursor?
Yes, sir.
Okay. So we have an alpha phase, we have a beta phase. It is, I mean, yeah, A and B, it is written in the question. You can take it for A and B as alpha and beta. And it is being said that there are 28% copper when the alloy gets solidified, and that happens at 779-degree temperature. Now, at this temperature, this is something called Lieber rule. I think you have heard about it. So this is a Lieber rule to find out the phase composition from a phase diagram. So like here you have all those things like alpha, this is liquid. So this becomes alpha plus liquid, here becomes beta plus liquid. Okay, so this is the lower critical temperature line. This is the higher critical temperature line, all these things. Now here silver is 100% and it starts reducing and copper percentage starts increasing and copper becomes 100% at this line. So this is similar to the iron carbon diagram you have seen, where carbon percentage increases, here copper percentage increases. Okay. Now at 779 degree, it is said that the alpha phase contains 9% copper and the beta phase contains 8% of argon. I mean 92% of copper, right? These points are being denoted by A and C, and this is the line for 779 degree temperature. Okay. So, and this is the point where it starts solidifying. Now, at this point, we draw a tangent to the particular curve. Okay, so we get where the curve cuts the solidus line and the liquidus line, whatever it is, that those points we take down and project to the abscissa. Okay, and then it becomes very simple, like you can see here. So here the alpha weight percent is given by this line PC divided by whole this line. This is lever rule. Okay, and similarly beta percentage is given by AB divided by this whole composition at this particular point, concentration of copper. So you can see like for weight percent of alpha we get BC. Now up to C we have 8% of silver, means 92% of copper. Okay, so 92 becomes the copper percentage at C, and 28 is the copper percentage at B. So this particular line we can take down as 92 minus 28. And similarly at A, at point A, when we project this down at point A, we find that we have 9% of copper. So the bottom line becomes 92 minus 9, we get 76%. In the same way, we can find beta also, beta weight percent. Okay, now the question has been asked, you have to find out at 717 as well as at room temperature. What happens at room temperature? At room temperature, of course, this particular metals or particular components of the alloy behave as pure metals. Is given in the question. Yeah, so at room temperature, they are pure silver and copper. So here you can take silver 100%, you can copper 100%, right? So here silver 100 means copper becomes 0. So using this as the baseline, A dash C dash, we can find out the weight percent of alpha at room temperature and similarly beta at room temperature. So do you guys get the question? Get the answer? Did you get it, Sahil?
So actually, I thought this was a binary isomorphous system, but
yeah, this is a binary system, right?
so
There
no,
are
I
two
thought it
components.
was isomorphous system, so I applied the formula wrong. This is eutectic system, right?
Yeah, this is eutectic system.
So I thought it was isomorphous, so I got
Yeah,
the
yeah.
wrong answer.
Okay, no issue. So did you use lever rule?
Yes.
Okay. So this is a eutectic system, and this is the thing. I think eutectic is not mentioned in the question. Yeah, that's great. So you got it now, na?
Yes, sir.
Okay. So practice such type of questions. This would be really helpful for you in your upcoming semesters as well as in GATE, if you are appearing for GATE, preparing to appear for GATE in future. And of course, if you are going for higher studies or research, then in core mechanical, you can't avoid this material science part actually. So how many number of atoms are present per unit cell in case of BCC crystal structure?
2.
Cool. And in FCC, do you know?
4.
You know how to find out those things, right?
Yes, sir.
Okay. So this is something an interesting topic called strain hardening. Are you exposed to strain hardening process? No? Somebody's mic is on. Can you please mute? Okay, so this is a concept of strain hardening, and this is one of the most important uh, phenomenon that is happening in all the metallic, in all the metals, almost in all the metals which are used for structural applications in automotive, industrial, infrastructure, civil, wherever you go. And without this concept, there is no definition of plastic deformation, there is no definition of bending, there is no definition of ductility, toughness, resilience, all are somewhere around related to strain hardening. So what is strain hardening? This is nothing but like for let us consider a particular material. Now what you do is you start deforming the material, you start hammering to go for a forging process, or you may also go for something called you somehow apply a compressive stress, okay, or a tensile stress you apply to that particular material. Yeah, Rajesh, I will come to it. Just let me complete this first. So what happens is when you apply some force or indirectly some stress to that particular material, what happens is the material starts deforming, and there are some things called defects, which by default comes in whenever a particular material is subjected to some manufacturing process. So these are called dislocations, okay, or these are actually technical terms used to define defects. So we have dislocation defects, you have screw defects, okay. So all these are out of defects only, which are generated during the manufacturing process, during the like processing of this particular material. Okay, so we have something called as edge dislocation, something called as screw dislocation. So in edge dislocation, what happens is out of the crystal structure of the particular solid, you have an extra plane of atoms. Okay, so that extra plane of atoms, what does it, when you apply force, suppose in this particular diagram, you start applying force from the left hand side. Okay, so what happens is uh, the first layer of atoms pushes the second, second pushes third, third pushes fourth, and then fourth we have a dislocation. Now the fourth moves to the fifth and it continues. Okay, now in other words you can say that this dislocation keeps on moving with continuing force from the left, and as a result of which there is a that this is a half plane extra row of atoms, and in the half plane there is a missing plane. There are missing atoms of this particular plane. So what happens is, if you consider that this extra half plane is moving to the, so these are called as, this is called a slip. Uh, the movement of this missing plane of atoms to this, to the left, this is called a slip. So what happens is, you have two particular planes slipping over each other. If you can visualize, we have two particular planes slipping over each other, and this is called, this is due to an edge dislocation. Now what happens is, when you're applying force, there are numerous number of such dislocations present in a particular material. So these dislocations keep on piling over one another. So one dislocation comes, then another comes, then another comes at the back of it, and this keeps piling over each other, and this finally resists the movement of these dislocations. Okay, like uh, the first dislocation provides some resistance to the second, which is at the back of it. Second provides some resistance to the third, and it continues. And due to piling up of these dislocations, we see that the material resists the applied force or applied stress. Okay, so this leads to some material resistance to deformation. And this phenomenon is called as strain hardening. So what happens is, with increasing stresses, there is not much strain after a particular point of time. When this strain hardening process happens, we say that the material gets hardened, and we don't find increase in the strain value with increasing stress. So that point is defined in the stress strain curve by the yield. After the yield point, we have a drop, and then it increases, the stress increases. Okay, that part is called as strain hardening, strain hardened part. So you can see in this particular stress strain curve, which has been obtained from some experiments by some researcher, you can see the black line and the blue curve and the red curve. These are for different materials, depending upon their sizes or their nature, ductile or brittle in nature, or the crystallographic structure. We can see different values, but you can see in all these curves, for all these different metals, you can see that at a particular point, this value is increasing, isn't it? At a particular point, this value gets increased, and this is nothing but the effect of strain hardening. Okay, so what influence does it have on the strength of a material? Can you answer? No, Rajesh, what are you saying is, that is one of the parameters of strengthening, that depends on grain structure, the grain size. Like if you have a smaller grain size, then you have a greater resistance to deformation. Okay, that thing is being explained by Hall-Petch equation. This is something called as dislocation effect. This is which gives rise to strain hardening thing. What you are saying, that is a grain size effect. Okay. So can you guys tell me, how does the strength of a material gets influenced due to this strain hardening process? Anybody? How does strain hardening influence the strength of a material? So what can you get from this particular stress strain curve? So you can see that the material can withstand a larger amount of stress without much straining. I mean, without much deformations. And what does that indicate? That the material has strengthened, isn't it? So strain hardening improves the strength of the material. I particularly mean plastic strength of the material. So you can deform the material to a larger extent now. The material can now withstand a larger stress. Okay, so strain hardening effect directly leads to increasing of the ultimate strength of the material. Okay. So now we have another numerical where it says that a cylindrical specimen is being given to you. It is having a dia of 12.8 mm. It is tensile tested. You know tensile tests. Do you know tensile tests? In the first year, in the there is a manufacturing lab, I think, in which tensile tests are being conducted. Hello.
Yes, sir.
Yeah. So the material has been tensile tested to fracture point, and after that, it has been found to have an engineering fracture strength of 460 megapascal. You guys have read engineering stress strain and true stress strain things.
Yes, sir.
So do you know which one is actually used in real life applications? Which type of strains or stresses do we consider? Like it is engineering one or the true one? And which one is more viable?
True stress strain.
Okay, so can we directly measure true stress strain from experiments? No, so that has to be found out theoretically. We can find out engineering stress strain, and from that, there are relations which has been developed for determining the two stress strain values. Okay, so this question says there is a fracture strength of 460 megapascals, and if the cross-sectional dia fracture is 10.7 mm, you have to determine the ductility in terms of percentage reduction area and true stress at fracture. You guys try. I give you some time, and then I will give share the solution. So have anybody got the answer to this question?
So the true stress is around 535 megapascal.
Okay. And did you find ductility?
So that's I'm calculating.
Okay. I completed. So have you done that, Sahil?
So just one calculation is remaining.
It's pretty simple, no? Okay, I'll show you the solution. So you have been asked to find ductility in terms of percentage reduction in area. So here I have mentioned specifically that you have to find it in terms of percentage reduction in area. You may not be given that in a question during exam. You have to simply understand what ductility means, or you can also be given find out elongation percentage. Both are same thing. Okay, so you have to find out that in terms of area reduction. Okay, so it's pretty simple. You have to find out the percentage as the ratio of the reduction in area delta A, which is given by the initial area minus the final area, and then you have to uh, take down that in terms of the original area. Okay, so here it was 12.8 mm, okay, of dia initially, which finally came down to 10.7 mm. So you can calculate the area, the initial dia and the final dia. and then find out the percentage reduction in terms of the initial die. Comes out around 30%. Okay, so now you have to find the true stress at fracture. Okay, so I have found out analytically. But there are also relations for true strain and true stress. If you have if you have read that. So the true stress can be given in terms of the engineering stress as the engineering stress into 1 plus E, where E is the engineering strain. Okay, similarly, the true strain can also be given as logarithmic of 1 plus engineering strain. So you can use those formulas also. And here I have found analytically there, so that doesn't need you to remember the formulas. Okay, so you find out the force given because the force remains constant, right, during tensile testing. The force is not changed. It is given, it is being subjected, the material is being subjected to the force until it fractures. So have the fracture stress, which is given as 460, and there is the initial area, which you know. Of course, you can't measure the area at every point during the tensile testing. So you do that in terms of the initial area, you find out the force which is being applied, and then you divide it by the final area to find out the true stress. True stress is always found out in terms of the immediate area of cross section. Okay, engineering stress or strain is found out in terms of the original area of cross section or dimension, whereas true stress or strain are always found out in terms of the immediate or final area of cross section or dimension. So this is how it follows. I hope you got it. I will share the slide, don't worry. You can take these problems down to check later on. So this says this is very important for any student, for any mechanical engineer. You have to understand the material behavior of different types of materials. Okay, like if it is a ductile, I mean ductile, there can be a plastic region or it can be perfectly elastic. There can be brittle materials. There can be rigidly plastic materials which don't have any elastic area of deformation at all. Okay, so here I have shown you some common material behaviors. Like first one is linearly elastic. There, the material moves up to the proportionality limit of elasticity only. Do you guys know what the proportionality limit means and what the actual elastic limit means? What is the difference, or is that same, the proportionality limit and the elastic limit?
The elastic limit is the point till where the Hooke's law is followed.
No, that is followed up to the proportionality limit, right? Stress is proportional to strain only up to the proportionality limit. You can perceive that from the name only. That is proportionality limit. Okay, so you have this curve which only uh, uh, behaves as a linearly elastic material. This is the curve for linearly elastic material. However, proportionality limit is followed by the elastic limit, where the material is still elastic. I mean, once you deform it, the material comes back to the initial dimensions. However, Hooke's law is not followed for that particular part. Okay, so the material regains its shape, but that is not proportionally. Okay, so that is the difference between these 2 points. So this is a material which behaves proportional. Okay, in which the stress is proportional to strain, and after that the material fails. Okay, so then we have elastic perfected plastic material, in which we have the elastic limit, but after that the plastic region is there. Okay, now what are these downward arrows being shown? These have been used to show you what is meant by elastic recovery. Okay, so when you have, suppose uh, uh, you have subjected a particular material to tensile test or to some tensile loads. Now the material deforms up to the elastic limit, and then the elastic region is gone and the material becomes plastic. Okay, now you remove all the loads of it at some point in the plastic region. So what will happen after that? Will the material come back to the initial position?
No.
Yeah. So some of the so the material behaves as a elastic plastic material. Like it happens that some of the uh, some of the deformation is recovered while some is not recovered. Okay, so this arrow is shown to show that only. In the right hand side of the part is the recovered strain, whereas the left hand portion is the deformed strain. Like this is the plastic strain, whereas the right hand part is the recovered strain. This much strain has been recovered. Okay, so this arrow is used to denote the plastic strain and the recovered strain. So this is the concept of strain recovery, which will you will again get in your strength of material, advanced strength of material, or anywhere in mechanical you will get this part. Okay, so this is about linear strain hardening, where I have already introduced this to strain hardening in an earlier slide. I hope you have understood. So the material now gets strain hardened at some particular point of time. Okay, so the stress increases much more than the strain. If you take out the slope at this point, okay, you can see that the stress part is much more than the strain part. Okay, so that is called as the linear strain hardening phenomenon. That is why the material is behaving in this way. If it was perfectly plastic, then this would be parallel to the x-axis or the epsilon axis. Now comes a rigid, perfectly plastic material. So it doesn't have any elastic part. It is completely plastic. Whatever much simple deformation you give, it never comes back to the initial position. Okay, now this is a power law. Power law means here you can see in these two cases that in this case you can see that there is no strain hardening. Okay, here you can see this is linear strain hardening, and here you can see this is non-linear strain hardening. Okay, so strain hardening need not be linear always. Uh, the material can behave in different manners also, and this has been experimentally found out that there are different laws to explain nonlinear strain hardening, like power law. Then there is something called uh, deformation law or something like that. So these are different laws. So here you have sigma equal to k epsilon to the power 1 by 3. K is the yield stress and our strength of the material, and then 1 by 3 is the strain hardening exponent. Okay, this exponent governs the strain hardening behavior of the material. This can be whatever, and for this can be different for different types of materials, and this is being experimentally found out. Okay, so this is a power law where the strain hardening has been governed as 1/3 power of the local strain. Then another thing is viscoelastic material. So do you guys know viscoelastic material? What does viscoelastic material means?
No, sir.
Okay, so viscoelastic material is something like they somehow exhibit properties of a viscous liquid as well as of an elastic solid. Okay, like any kind of polymers, you have thermosteels, thermoplastics, not thermosteels, it's thermoplastics. Okay, there you can, or thermosets. Okay, there you can find this viscoelastic property. Like when you melt a plastic, it becomes almost a liquid in no time, less time. Na? So there is a boundary where it behaves as both it behaves as viscoelastic. I mean, semi-elastic. It is also having a liquid behavior, viscous liquid behavior. It is also having an elastic solid behavior. So this type of materials are called viscoelastic materials. So now we come to a question where it says that a perfectly elastic body you are given, which one is the best characteristic of a plastic or sorry, elastic body? So it is pretty simple. You guys know that when deforming force is removed, it comes back to its original shape and size. So now we have the property. This question says the property of material by which it can be beaten or rolled into thin sheets, which is the property called? Yeah, malleability. But can you tell me the difference between malleability and ductility?
So ductile materials can be drawn into thin wires.
So malleable materials cannot be drawn.
So they can be rolled into thin sheets.
So you mean they cannot be drawn, right?
Yes, sir.
No, that's not true. They can be drawn, but in case of ductile materials, they can be drawn to a much higher extent than these ones. And do you know why so? So
No,
ductile, tell me.
don't know.
Yeah, so malleable materials in which you can consider it as a plate or a thin sheet, okay, which has a larger surface area than its thickness. We can hammer it or put pressure it from the top so that the length and breadth dimension increases and the thickness dimension reduces, right? So what happens is is uh, the material has higher strength, higher compressive strength. Okay. So what happens is in the thickness region, it offers more resistance. Okay. So that's why the ductility is less and malleability is more. However, in case of ductility, the opposite happens. The material has more resistance towards, sorry, uh, I have told you the opposite thing. Okay, so in malleability, in this malleable materials, they have more resistance to tensile deformation, whereas in ductile materials, they have more resistance to compressive deformation. As a result, ductile materials can be drawn to a larger extent, and malleable materials can be forged or reduced in thickness to a larger extent. Some materials are there like they are both ductile and malleable to some extent. They have both the properties. So, do you think toughness and resilience are of same significance? Do both of them mean the same?
So toughness is the energy absorbed by a material just till it reaches the fracture point.
Hmm. And resilience? So, resilience is the energy absorbed up to the elastic limit. Okay. So you can see here from the diagram directly from the stress strain curves. The first one is for toughness and this one is for resilience. Both have their own significance according to the application. Okay, and modulus is nothing but when you divide it by the volume. When you take the energy per unit volume, it becomes modulus of toughness or modulus of resilience. Or you can also say strain energy. Okay, so it is half into stress into strain. Okay. So in questions, you may be given a particular strain hardening law or a particular stress strain relation, and you may be asked to find out the toughness or resilience value, and you may be asked to explain which one gives significance for that particular application. So these things you should know. So now we come to our final topic of today's session. You have to find out the edge length for different types of crystal structures. Such type of topics has been taught to you, no?
Yes, sir.
Yeah, so you know how to calculate the edge length for SCC, FCC, BCC, or HCP.
Yes, it's with respect to the radius we calculate.
Ah, so let me take you through. So this is a simple cubic structure. As you know, we have 4 atoms at the 4 corners, and there is nothing in between or at the faces. So you have half of the dia of one atom here and half of the dia of other atom here. Okay, so the dia is d equal to 2r. So you take half of both to get the final dimension. Final edge length is 2r, which is being shown here. And then comes this. This is a structure where you have to consider 2 relations to find out the edge length. So first one is like there is an atom, because this is a BCC structure, it is a body-centered cubic. So that simply means it is a cubic structure with one atom at the center of the body. This violet one you can see here. So what happens, you can take out a plane which which meets the 2 points diagonally, meets the 2 diagonal entities of the particular lattice. Okay, so then you have an atom in the mid and 2 atoms in the corner. So you have twice radius of one atom at the mid and half the dia, I mean r plus r for the 2 atoms in the corners. The total you have 2r plus r plus r is 4r, represented by this green line. And this one length is edge length A. And then this blue line, let's suppose this is a diagonal of length D. Now, to find the diagonal, you consider the bottom face, okay, of the lattice. Then here you have this particular triangle, blue line, and these two red lines, the sides. So the using this particular triangle, you can find out the edge length. Okay. So here you can find out the value of D as root 2a using Pythagoras theorem, and then you can put it back in this relation, considering this diagonal section, and from that you can find out like a square plus d. You replace it from root 2a here, which you find out using this triangle at the bottom face, and using that you can find out the edge length is 4 by root 3r. So then you can find out this atomic packing factor, APF also, and the volume of using the volume of atoms in cube. Once A is found out, then these are simple. Okay. So similarly, you can see the same thing happens for FCC also. Here it is rather simple because there is no body-centered atom. All the atoms are at the corners and some at the center of each face. So, okay, so if you consider this as a face, then this green line is given by 4R. Okay, and this red line is A, and this red line is A. So get using Pythagoras, simply 2a square is 4r square. This is the hypotenuse and these are sides. And using simple Pythagoras, you can find A equal to 2 root 2 R. Okay, and the same way you can find the volume of atoms, cube, divide it, and the ratio becomes 74%. So the last one is a hexagonal packing structure, close pack structure. It is also, you can consider it as a hexagonal prism. So area of the triangle, not triangle, area of a hexagon you can find out using these geometrical relations. Okay, so if this whole thing is A and you drop a perpendicular from the center, you get a bisection here as A by 2 and A by 2. Okay, and these are A because the angles remain same, 60 degree each. So the sides also remain same as an equilateral triangle. Now using simple geometrical relations and using Pythagoras theorem here, you can find out that the area of triangle is root 3 by 4 a square. So you know that is the area of an equilateral triangle. Now there are 6 such equilateral triangles, and you multiply with 6 to get the area of the hexagon as root 3 by 2 a square. And A you found out from this relation. Okay, here you can see the edge length is simple to R because there are 2 atoms at the 2 corners. Is same as simple cubic structure. Okay, simple cubic crystal structure. Now you put the value of A from there, and you can find out the area of hexagon or the volume of hexagon, whatever you like. Okay, so this question is clear.
Yes, sir.
Cool. So there was one question in the chat from Rajesh. Okay, it said which of the following contraction type is observed by shrinkage allowance? Such a question has already been discussed, I think, Rajesh. Still, you have to actually, it is said that which type of contraction is being observed by the shrinkage allowance. So you have to take care of the, you cannot take care of liquid shrinkage, right? And you have to take care of the shrinkage which is maximum. So you have 3 shrinkages. One is at when the liquid becomes solid. One is at when the during the solidification, and one is after the solid has solidified and it comes down to the room temperature. Okay, that is called solidification shrinkage, and that happens to be the maximum. Okay, so you have to take care of the solidification shrinkage only. So you can choose it from the options. I hope you got it. Okay, so do you guys have any doubts? So was this session helpful? Like, could you learn something out of what has already been taught to you? Could you gain some new concepts out of this session?
Yes, yes, sir.
Okay, great. So this presentation slides will be made available to you through a Google Drive link. And this video will also be uploaded over YouTube. And the link will be shared to you from NPTEL team. If you guys need these questions or these concepts in future, you can just look at whatever you want, and the slides or the video will always be there over YouTube and my channel. Okay, these links will be shared to you from the NPTEL side. So when is your exam for this course?
In April, I think 30th.
Okay. And how many students have registered here? Around 6,000-7,000, I think, man.
Yes, sir.
Yeah.
So you can post some questions if you have, anybody of you, or else this is the last question. We'll wait for, there is still 20-25 minutes left. So you can wait for that.